This is question number 12 from chapter 23. It reads, some rearview mirrors produce images of cars behind you that are smaller than they would be if they were flat. Are the mirrors concave or convex? What is a mirror's radius of curvature if cars 20 meters away appear 1/3 or 0.33 times their normal size? I put a little image of that I grabbed off the web here. We can see the little inscription that we're so familiar with on the bottom of that mirror. Objects in the mirror are closer than they appear. Most of you should have enough experience in class so far to recognize this as a convex mirror. And convex mirrors always, regardless of the position of the object relative to the mirror, produce images that are smaller, upright, and we can see that the image of this car here is upright but smaller, and they happen to be virtual. So let's take a look, a real quick look at the ray diagram here. So I've got a bunch of different rays. I've got one that's parallel to the principal axis. That's going to reflect in a line that is related here to this line from the focal point. So this is our reflected ray here. And then I have a ray that would have gone through the focal point, so we can see that it's on the way. And if I had continued it, it would go through the focal point. And that ray is going to reflect parallel to the principal axis. And finally, I've got my ray that strikes the mirror at the principal axis, reflecting below the principal axis at that same angle here. And so these diverging rays, which I'll label 1, 2, and 3, these diverging reflected rays, when viewed by an observer on this side of the mirror, appear to originate from behind the mirror. Let's go ahead and track those lines back now. So if I track this line back, a little off target here, and then finally here, we see that they all converge at some point behind the mirror, producing the illusion that the image is here and upright. We can see from the sketch that it's smaller in relation to the object, but it is virtual because it's behind the mirror. Of course, this is opaque, not allowing light to pass through it. So this is a perception from a viewer on this side. Okay, so we've identified the answer as a convex mirror, which is one of the questions that's asked. The second question is, what's the radius of curvature C? We know that that's related to the focal point, and that that twice the focal point is equal to that center or radius of curvature. So I'm going to take a look at some useful equations that I've written out ahead of time down here. We've been given the problem, the distance to the object and the magnification. We've been given these two guys. And eventually, in order to relate the magnification equation here to the thin lens equation, I'm targeting this. This is what I want. This is the focal length. And so we can see here that the missing piece, kind of the solution to this problem, is finding the distance to the image. And if I know the distance to the image, I'll be able to plug that in here. This is already known, and solve for f, which is what I'm looking for. So that's my plan of attack. I'll start with the magnification equation, negative di over do. And I'll just plug things in. I'm going to solve for di, so this becomes do times the magnification is equal to negative di, and plugging these numbers in, this is going to be 20 meters times the magnification of 0.33. Remember that magnification is unitless, it's units of meters over meters, is equal to negative di, or I can divide both sides by -1 or multiply by -1 and bring the negative sign on that side. That's going to give me an answer of negative 6.60 meters being the distance to the image. So what does this negative sign mean? Well, it means that if you know the sign conventions, it means that this distance here is 6.6 meters, but the negative sign indicates that it's virtual, and so therefore it's behind the mirror. Positive 6.6 meters would be on this side of the mirror, which of course it's not since it's a convex mirror. All right, now that I have the distance to the image, I'm ready to move on to step 2. Step 2 involves using the thin lens equation. I'll go ahead and start with 1 over f is equal to 1 over do plus 1 over di, and I'm immediately ready to substitute. So that becomes 1 over f is equal to 1 over the distance to the object given to me in the problem. It's positive 20 meters plus 1 over negative 6.6 meters, which is the distance to the image and what I found in the previous problem. When I run this through my calculator and solve for f, I get 9.85 meters. And I forgot my negative sign here, so let's remember to put that in. Now, negative 9.85 meters, why is it negative? It's negative because this is convex, and by definition, the focal point of convex lenses, the focal length, is negative. This isn't my answer, though. The question was asking for what the center of curvature is, so I should recognize that the center of curvature is 2 times the focal length, which is going to give me 19.7 meters. And that's what was being asked for in this particular problem, and that's the answer to question number 12.